Hey everybody, welcome back to A View from Earth, the official podcast of the Fiske Planetarium at CU Boulder. I hope everybody's doing well and staying safe out there. My name is Tara. I'm a planetary scientist and a CU alum, also a presenter and outreach coordinator for Fiske. And as always, I have Colin here with me. Hi, Colin.
Hey everyone, I'm Colin. I also work at Fiske as a presenter when the building is open, and I'm an undergrad studying astrophysics at CU.
Yeah. So today we are talking with Dr. Carolyn Crow all about moon rocks. She is a geochemist who studies rocks on the moon to tell us about the history of the moon, some of the cool things that we can learn about the surface and the subsurface, and maybe even some habitability issues. It's going to be super cool. I'm really excited. I thought it was a very fun interview. What did you think, Colin?
Yeah, it was super cool. You know, there was a lot of talk that typically with these interviews, my vocabulary does not get exceeded by what the interviewee is saying, right? Like, because, you know, in the field, you just have like, you know, the vocabulary and you just know what the words mean. But today, well, today being the day that everyone will be listening to this at the same time, which for us was actually yesterday when we did the interview, it's all geoscience, right? Which I have I just have not really done any of that. And so there were so many words. Even at one point I stopped the conversation and I was like, can someone please tell me what this word means? Because you keep saying it and I have no idea what that is. And so it was kind of a cool experience I really feel like I learned a lot, even just like vocabulary wise, just by like being in the interview, not to mention how much insight all of the guests bring. So
Yeah, it's jargony just like any other science, I think. Geoscience has a lot less acronyms than astronomy, so I give them that. We all use just very long, like complicated words rather than making it into some crazy acronym, which I kind of dig. But I liked, we also had a conversation kind of off the air afterwards that I thought was fun about the differences between studying planetary science like geophysics and surfaces and atmospheres and things, and looking at like astrophysics, like cosmology, looking through telescopes and stuff like that. Because I think as geophysicists and, you know, planetary scientists, so much of our job is looking through like spacecraft data. We don't do a whole ton of like actual telescope observations, which people don't always realize. Like my job has zero telescope hours in what I do, which I like personally. I didn't know that I would, but I do.
Have you done much observing with telescopes, Tara, yourself?
Only for classes, really. And like I have a little telescope that I take out and look at things. I looked at the comet when that came out, and occasionally, like if friends come over and want to take the telescope out, we'll go like look at the moon. I've taken some cool pictures of the moon like through my telescope eyepiece. But otherwise, no, like Earth-based observations are hard, man. Like,
now, when we were having this conversation, which you as the listener will hear in like, what, an hour-ish, John, you mentioned that you kind of are more interested in the astrophysics side of things. You know, I guess I emphasized the wrong word, astrophysics, not astrophysics, because there's still geophysics.
Yeah.
Where do you know, what's your motivation for that preference?
Well, not specifically the astrophysics, but telescope operations definitely. I love just being able to be at an observatory late at night. I think it's really, really cool, and that having that opportunity continues to reinforce my enjoyment of astronomy. Just feeling that connection to the universe. There's a couple pieces of glass in the way, but you're looking at these things directly rather than through an instrument captured via a little chip that's reading the light and then transferred into ones and zeros and then retransferred back into light. I just really enjoy that feeling of connection when you look at something directly through an eyepiece.
And it's interesting that you mentioned the connection, because I think for someone like Tara, and of course, correct me if I'm wrong, geophysicists and geochemists get their connection from, from literally holding the samples, right, that get returned, and dealing with, actual pieces of rock, for example, that came from a spot that was not the Earth.
Yeah, I think so. Like if I could, get a chunk of ice from Europa, that would be amazing. I don't, I don't have the option of holding pieces of the moon that I like to study, but yeah, for like moon rocks and things, that's so freaking cool. Like she was, she'll tell you in a minute how, there's so much cool stuff that you can learn when you have something like right in front of you and you can look at it rather than just, like the problems that I have where my instrument is super old and the resolution is terrible and the spectra are all wonky, and it's not the same. You gotta do a lot of workaround and a lot of extra stuff.
Right.
When I would much rather just like be able to pick something up and eyeball it.
Sure. Well, and I think it's interesting that just different people are drawn to different ways of connecting, and so and then of course my version of that right now is just like doing a whole bunch of homework and reading the textbook. That's my way of connecting with the universe at the moment as a student. So
and there's people that do that too. I work with a guy who's like, data analysis is his jam, and like instrument calibration, he is all about it, and he's not really terribly concerned with touching a planet or doing a lot of observations. He just wants to make sure the data is the best that it can be, and that's his connection to the universe.
Yeah
Which takes all kinds, man.
Yeah, absolutely. Very cool.
Well, shall we jump into our interview with Miss Crow?
I think we shall. Yeah.
All right.
Let's do it. All right. So now we are talking with Dr. Carolyn Crow, who is an assistant professor of geosciences at CU Boulder. Her work focuses on understanding the evolution of planetary crusts through chemical analyses of first-hand samples like meteorites and moon rocks. Part of her research also supports nuclear forensic projects that aim to understand the signatures of underground nuclear explosions and characterizing materials for the International Monitoring System. That is so much cool stuff. Dr. Crow, thanks so much for being with us today.
Thanks for having me. I'm excited to talk to you guys.
We are stoked. So one of your specialties is looking at the composition of moon rocks that are brought back to Earth from different Apollo missions, which, for anyone who doesn't know, the Apollo missions were the moon missions where we went to the moon. What sort of things can we learn from these samples aside from just what they're made out of?
Yeah, so we can learn a lot of different things from the Apollo samples. So one plug I'll put in right at the beginning is that, sample return, and I think maybe we'll talk about this later, but the samples that we have got back from Apollo, right? We've had these samples for over 5 decades now. So we've done 50 years of research on these samples, and we are still learning amazing new things from these samples. So the materials that you get back from these missions, although maybe that's, it's high risk, high reward type of science, but basically they've revolutionized our entire understanding of the solar system and have fueled 5 decades of research and will continue to fuel probably 5 or more decades of research to come in the future. So these are very, very, very valuable samples that we have to work with. And we've learned all different kinds of things. So the research that I mainly focus on for understanding the chemistry is I'm really understanding the timing of processes. So what we call geochronology, right? So the geo is the geology and the chronology is the timing. So I'm interested in understanding the timing of events that happen on the moon. And that ranges from when did the moon form, right? When do magmas form on the moon? How does the evolution of the moon magmatically occur? And then also to processes such as impacts, right? You look up at the surface of the moon, you see all these impact craters. when did they happen? Did they happen recently, a long time ago? How many, how often? Those kinds of questions. So anything that you want to put a timestamp on, that's where I come in. So that's my field of research in particular, but we can learn all interesting types of things, right? If you think about the moon sitting up there, being exposed to our space environment without an atmosphere, right? There's not, Earth's magnetic field is not protecting it. It's just kind of sitting out there, and it's just this record of everything that our Earth-Moon system is experiencing. And so it's kind of this witness plate. We can learn things about, how did water and volatiles, get delivered to the Earth-Moon system? Did we have it originally, right, when we formed, or was it delivered by comets and other meteorites that are hitting the surface? What's the solar environment like, right? You can probe the particles that are being put off by the sun by looking at the samples on the moon. So there's a huge range of applications or things that you can learn about just by looking at the chemistry of these samples.
So just out of
sorry, go ahead, Tara.
Just out of curiosity, do you know about how much stuff was brought back from the Apollo? Like how much, you have like a weight estimate of how much moon sample we have or had to begin with, maybe?
Yes, I'm going to do the conversion though, because I don't want to do it in kilograms. Because that's better for the audience. So all told, all Apollo missions, so we have samples from 5, right? We've got 11, 12, 13, not 14, 15, 16, 17. And altogether, we brought back 842 pounds of sample. So wow. That's a lot of rock. So it's also a combination. It's not, all rocks, right? There's rocks, or what we think of rocks, but they're different on the moon. And we have lots of soil. So there's, that's kind of like the loose grain regolith that's on the top. And then we have drill cores and drive tubes, which are basically samples that go down in depth, up to a couple meters in depth. Yeah. And there's still a lot left. There's still a lot of samples available that we are actively doing research on. There's these new never been opened before samples that are being opened up. I don't know if you guys have heard about those on the news. So this is called the ANXA project. So it's the Apollo Next Generation Sample Analysis. And basically what these samples are, these samples that were specially curated when they were returned to the moon. And by specially curated, I mean we are storing them differently than we do most of the normal samples. So usually what happens is the samples come back, they are stored in dry nitrogen at room temperature. And so they're in dry nitrogen, so they're not reacting with our atmosphere. But there's some other samples that were specially curated in terms of, they were frozen in addition to being stored in nitrogen, or they were stored in another inert gas, or in a vacuum. And one of the questions that we have is, how does the storage of these samples long-term for 5 decades influence the chemistry and the composition that we're measuring? And we're checking to make sure that the way that we are storing these samples isn't influencing the data that we are getting. And this is highly important for all of the sample return missions that are coming up in the future. So that's a project that's currently going on right now that I am participating in, and doing geochronology and looking at geochronology of some of the samples.
And kind of jumping back, well, actually, you just said it just now too. When we consider geochronology, right, figuring out the timing of these events, surrounding or regarding rocks, essentially, when you set out to answer a question, when did this happen, or how old is this, etc. Like, what is a standard approach for? Okay, well, you have this rock here in the lab, or maybe you have some data that we took observationally about the moon. How do you use that then to put a time on some event?
Yeah, so the timing we actually get from isotopic abundances, but you did touch on something that's important, which is you want to have some understanding of the sample itself, right? Where it's coming from, any other constraints that we might have of the timing of such events, right? Because the way that geochronology works is basically we capitalize on radioactive decay, right? So you have an element like uranium that decays to a stable non-radioactive element, lead, at a very known, very well understood rate. So if you can measure how much parent, how much daughter, you can understand how long it's been decaying, right? But all these different chronometers that we have different half-lives and different age ranges, right? So you can have ones that decay really fast, you have ones that decay over long periods of time, and ideally what you want is you want to have a chronometer, one of these systems, that has a half-life close to the age that you're measuring. So instead of going in and trying this one and this one and this one and this one, you want to be able to go in and say, okay, this is the one I want to use. It's going to give me, the age range that I want. So that's like one consideration. The other consideration is that there's also an influence of temperature on a lot of these systems. So you want to, and that might be of an advantage. So for example, if I want to date an impact event is a very high temperature event, right? So I'm going to want to use a chronometer that's A, in the age range that I want, but B will also be sensitive to that impact and will get reset. Basically push, if you've got that timer on your phone, right? You push the reset button, you go back to 0. You want that sample to push 0 so you can get really good age. So yeah, you kind of use all of the information together. And then it also, you have to tie in the sample chemistry, right? Because if you're wanting to use the uranium lead system and there's no uranium in your sample, well, then you're not going to be able to measure it because it doesn't exist in your material. So there's lots of different considerations to take into account.
So I assume a lot of these things that we're learning about these samples from the Apollo missions are also relevant to the upcoming Artemis program that's going to put humans back on the moon. Do you maybe have any examples of how our knowledge of the surface and the history of the moon is beneficial to this human exploration?
Yeah, one of the key ones is, as I kind of touched on before, that the moon is exposed to the space environment, right? Unlike here on Earth, where we're protected by an atmosphere and a magnetic field that saves us from getting hit by a bunch of high energy particles or meteorites, that's not the case for the moon. And so when we send people to the moon, this is a hazard, right? This is something that they are going to be exposed to. So understanding what that space environment is like is going to be really important for designing, shields or barriers, or putting constraints on how long can someone be on the moon before the radiation environment is detrimental to their health, or what are the health risks of being on the surface of the moon. So that's the first one. There's another really interesting one that people don't often think about, which is actually this lunar soil, or this regolith, right? Lunar soil is not like beach sand. You go to the beach and, it's nice to put your feet in and it's all warm, and this is not the case on the moon. So the soil on the moon, instead of being produced like when you're at the beach, right, it's turning in the waves, they're getting nice and smooth. On the moon, it's basically shards of glass and minerals that have been chipped off in a way of rocks by the impact process. So basically, if you look in a microscope at lunar soil, it looks like little shards of glass. And so it sticks to everything. So, it sticks to, you can look at some of the pictures, and I wish I brought some up with me, but you can look at the pictures of the astronauts and their suits are covered. You can, look at the transcripts of different interviews with them, or how they're discussing collecting samples. Once they got back into the capsules, no matter how much they cleaned off the suits, it would get in the air, and it would irritate their eyes, it would irritate their lungs. It made it very uncomfortable. It influenced the ability to use some tools, and, you know, sealing canisters stuff. So the lunar soil is probably one of the biggest technical difficulties is going back to the moon, because it's so hard to deal with, and it is, you know, it is a health hazard. Breathing that in, it could have very bad health effects if you're doing that on a daily basis. So these are areas of research that, you know, is only going to be enabled by looking at samples or sending robotic spacecraft back to the moon.
That's kind of my experience with sand in general, is just that it gets everywhere and it keeps you from doing things, and it's awful. But little tiny shards of glass sounds way worse.
Yeah, yeah, different level.
Yeah.
When Apollo, you know, first was starting up, you know, and we're, you know, putting, you know, people on the moon for the first time, did NASA or you know, anyone on Earth know that that's how the regolith or the lunar soil was going to be, or was that a big surprise? They got there and they're like, wow, there's so much small glass everywhere that we didn't plan for.
Yeah, so that's a really interesting question. And it, you know, it's a little bit of a historic perspective. So this question of how did craters form on the moon was not entirely settled until the Apollo missions. So prior to the Apollo missions, I'd say vast majority of people agreed that it was most likely impact cratering, but the theory of them being formed by volcanic processes was still being considered. So, you know, I think there was a sense that this regolith was going to be the product of an impact process, but I think maybe to the extent to which the lunar soil is the way it is and how difficult it would be technically, it was you know, not well understood. They did know enough that you know, this top layer of the moon was not very compact, right, and was, you know, because of some of this impact gardening, and that was the reason that they sent robotic spacecraft prior to humans, because they didn't know if they were going to land on the surface and then sink in meters and just disappear, right? Just because the density of the material is a lot, you know, is a lot lower. And so they sent the spacecraft up and it didn't sink in. And part of that is due to the fact that this material is just so irregular and sticky that it can hold itself together. So yeah, that's a really interesting question.
So is that to say that, you know, before today, where we, you know, have a much better understanding than we did when we were asking these questions initially, is, I guess I'm not very acquainted with the geosciences. Are craters and volcanoes hard to distinguish just visually speaking? You really have to go up close and personal with them before you can say definitively that this was an impact crater versus a volcanic crater?
On Earth, we have a lot more volcanic craters than we do impact craters. So you're probably pretty well off assuming that it's not an impact crater. But yeah, so the calderas, which are these basically collapsed volcanic craters, depending on the size range, can look similar. They do have a different depth to diameter ratio, and this was something that was kind of recognized prior and used as a way to say this is probably not, you know, volcanic. But so it's much harder to figure out if something is an impact crater on Earth than it is if it's volcanic. And the key way that we figure out if something is an impact crater is actually looking at, we're looking for shock metamorphosed minerals. So minerals, if you squish minerals together, and especially in very rapidly, right, in a shock environment where you basically smush them together, you can get these basically high pressure structures that are different than what you would find in regular environments. And these only form in shock environments. And those volcanic craters do not have those types of shock levels associated with them. So yeah, if we are trying to identify impact craters, we look for shock metamorphosed minerals at that site.
Got it. Thank you. So I'm going to ask a question that you've probably answered a billion times, but we got to know, how does understanding the surface of the moon or Mars or asteroids or really anything that's not the Earth benefit us here on Earth? Maybe barring because we're curious, right? That's kind of the obvious answer that, oh, well, we just want to know. What other benefits do we reap as, humans and as, civilization on Earth from learning about these other things?
Yeah, that's another good question. Yeah, so a lot of the things that we're interested in here on Earth, right? Like understanding Earth as a system, right? How does even the big picture questions of, how did the Earth form? How did the moon form? What's the environment experience since then? Questions about how did life emerge? What are the key influencers for life surviving? All these kinds of things, right? Habitability of the planet, all those types of questions benefit from having an understanding on a broader planetary context, right? Not just our Earth system, but we can learn a lot about Earth, how by studying the moon, because that space environment, right, of what are we getting hit by? What are we getting hit by right now, right? That's an important question. What's the space environment like? Lots of those questions. But then looking back at like mass extinction events and, trying to understand, does that relate to something on a larger dynamical scale within the solar system? Does that happen on a periodic time scale? These kinds of questions, that we're trying to, that help us understand our environment locally. We need to understand more planetary what's going on. So there's relationships there. And then also, a lot of the thinking about it on a technical side, right? A lot of the technology that gets developed for understanding planetary materials have applications elsewhere. That's where my research in nuclear forensics comes with, because you produce the same things in supernovae that you do in nuclear explosions. So you use the same kinds of chemical analyses, you use the same kinds of laboratories to do these kinds of experiments. And so if you learn something in one field, it becomes applicable to the other. So there's kind of these offshoots of benefit that you might not think about, but it's that innovative aspect of science, right? Like it's all interconnected at some level.
I've heard it called, I think, the Star Trek effect before, where it's like technology that we devise to go to space is often, that's how we got cell phones or, stuff like that. That's how we got tiny microchips, because we first developed it for space travel or whatever.
Mm-hmm. Yeah, and it's interesting. I did my postdoctoral fellowship at the Lawrence Livermore National Lab, and all of the people that study nuclear forensics there are also cosmochemists, or at least do these kinds of chemical analyses. We are either measuring meteorites or some other weird material in the lab. So it's yeah, they're very interrelated in terms of how you actually do the science.
And it almost feels kind of like self-fulfilling or perpetuating, because, you mentioned at the beginning, we get this sample return and now we have this thing here, but maybe we don't know all of the ways that we can learn from it. And so the more that we learn from it, and the technologies that we develop to analyze it, now open new doors to do even more, testing and experimentation. And so it's just kind of this like snowball effect where you're like, so many doors are opening, because the more we learn, the more we can learn, which is super cool.
Yeah. And that's, and we are lucky that, or fortunate that, early on in the Apollo program, when the samples came back, they realized this, right? And so samples have been set aside. There's this ANGSTA program with the specially curated ones, but there's also a reserve of samples that have never been opened before, right? Basically with this idea that technology will get better. And so we should not necessarily dive in right at the beginning. And I think a lot of people are, especially in my science community, agree that, you know, now is actually one of the times to start cracking into them, because we have really cool new techniques. Like we can do CAT scans of the samples themselves to try and understand or get an idea of the different kinds of materials within the rocks. And then you can do targeted special curation. So basically all the, what you think of like rocks from the moon are not like the rocks that you pick up in your backyard. They're what we call breccias. And this is also a process or a byproduct of this impact process, where it's basically a bunch of rocks that have been chipped off other boulders, put together into another rock because of an impact, impacted again, broken up, re-conglomerated again with some more materials. So you end up usually having multiple, what we call lithologies, or multiple kinds of rocks within one hand sample that you pick up. And so if we can do these CAT scans and get an idea of what material is in there, people can actually start requesting and saying, hey, I want a sample that has this kind of composition and this kind of size, or I need something that has, you know, this concentration of whatever mineral. And you can actually do the CAT scan and you can do a precise cut and get somebody exactly what they need, as opposed to the way that we have carried in before, which is you kind of cut it open, you see what you get, or see what's on the surface and go from there. So that ability to do kind of targeted curation, in addition to advances in laboratory capabilities, make this a really good time to, you know, really doing a lot more detailed analyses of these samples and going after questions that maybe we couldn't answer before.
That's super cool. I really like that idea. One of the questions that I get a lot, and we wanted to ask you too, is, you know, we use meteorites that are found here on Earth to kind of understand the chemistry of places that we think they came from, like Mars or the moon or what have you. How can we tell where a meteorite came from if we don't have direct samples from that place? Like, how did we know that a meteorite came from Mars before we actually went to Mars?
It's red. Easy. Done.
Very red. Under the fusion crust. Yeah, interesting question. So the first way that we were able to identify meteorites from Mars was actually looking at trapped atmospheric components. So the atmosphere of Mars is very different than the atmosphere of Earth, right? And when a meteorite is ejected from the surface of a planet with an atmosphere, during that impact event, there is little bits of atmosphere that are implanted into the sample during the shock process, and it gets trapped. And so if you look at the gases that are trapped in Martian meteorite samples, they look like the atmosphere of Mars. And so that was the first way that we were able to identify that these samples were probably coming from Mars, or say these are coming from Mars. And now we don't have to do that because we also use now this other constraint looking at the oxygen isotope abundances. So basically you have different isotopes, which are basically elements that just have different numbers of neutrons in the interior. It's oxygen, but it's got an extra neutron. Every planetary body has a different oxygen isotope composition. So there's 3 oxygen isotopes that we look at. And the Earth and the Moon are the same. So we kind of, in geochemistry, think of this as like the planet's fingerprint, right? Your oxygen isotope is your fingerprint. So the Earth and the Moon have the same fingerprint, which gives us clues about how the Earth and the Moon formed. Mars has a different fingerprint. The different asteroid parent bodies have different oxygen isotope fingerprints. And these variations depend on, you know, where you form in the solar system, and there's all these different ideas about why it varies. But now, because we know these samples are from Mars because of the atmosphere, we can measure the oxygen isotope composition of samples and then have a better understanding about where they come from based on that.
Very cool. So, a bit of meta podcast stuff here. Tara and I have this document of questions that we're both looking at, right?
Mhm.
These are questions that Tara typed up for us and to kind of, guide our conversation. And I was just in the process of commenting on a question that we have. And so the question that, I would ask next is, what advantages does studying direct samples have over techniques like remote spectroscopy? And I think that we've kind of touched on that a little bit throughout the conversation, right? We've talked a lot about sample return and why, we like to do stuff here in labs on Earth, partially because the stuff is here to do it with on Earth, right? And so we have about 20 minutes left of our time here. And so we do have a couple of what we call Capcom Q&A, which is where people ask us questions, and then we ask you what those questions are, and then you answer them. And then someone gets to hear, oh, wow, my question was just answered by an expert. That's pretty cool. So before we get into this, I should ask Tara, are you okay if we jump into Capcom and then we'll come back through and do that last question before we wrap things up? Is that all right with you?
That is fine with me. Yeah.
Excellent. Very good. Okay, cool. Well, so let's kind of jump into this Capcom Q&A question area. So these are questions that are asked by real people that knew you were going to be on the show and were like, hey, let's ask. So Ray from Austin is asking, does the composition of moon rocks vary by location, or are they all mostly the same?
That's a good question. So there's basically two main large scale lithologies on the moon, right? So if you look up at the moon, you see light stuff and you see dark stuff, right? And that's a compositional variation. So the light stuff is what we call the northacitic highlands. This is close to the original crust of the moon, if not the original crust of the moon. So it's very light because it has this mineral anorthosite in it. So it's very what we call felsic because it has all this anorthosite. And then the dark stuff is basically what you can think of as like flood basalts. So this is a lot more mafic, iron-rich material. It's basically flooding in these impact basins. So depending if you're on the mare or the highlands, the material is going to be very different. And also an interesting to note is that the far side has very little of this darker material. So it's mostly this highlands material. So on a large scale, you have these big compositional variations. And then on a finer scale, you do have things, you have, it's more in kind of trace things like titanium concentration will change. Then we have these kind of really interesting kind of magmatic bodies or episodes on the moon, right? We have this one, my favorite one is creep, creepy samples. So these are samples that are enriched in potassium, rare earth elements, and phosphorus. So it's the KREEP, creepy. And you get samples that are highly enriched in that. You also get some samples that are highly enriched in magnesium. So there are variations in the composition between samples in different locations, for sure, but maybe not at the level you would think of.
Not quite as bad as like here on Earth where we have, billions of different kinds.
Yeah.
So D from Portland wants to know, does cosmic ray bombardment change any measurable surface properties of lunar rocks?
Yeah, so actually we do what's called cosmic ray exposure dating. So yeah, cosmic rays are really high energy, and at least what I'm interested with them is that when they interact with a sample, right, if you have a cosmic ray and it hits an atom, you can knock off a bunch of material. You can knock off a bunch of protons and neutrons. And, usually that byproduct is radioactive and it'll, decay to something that's a little more stable. But basically what you can do is it'll produce these things that are not normally in the sample, and you can measure those and you can get an estimate of how long a sample has been on the surface for. And that's very interesting because that will tell you about kind of the more recent impact history, right? You can look at some of these long-term chronometers to try and understand things that happened billions of years ago, or you can look at things at exposure ages from cosmic ray exposure to try and understand how long it's been sitting on the surface. And so one of the things that I'm interested in doing in my research is kind of combining all these different systems together to hopefully at some point be able to take a sample and say, okay, this sample formed 4.2 billion years ago in this kind of magmatic event. It was then, impacted by this large impact basin. It ended up in the ejecta environment this far away from the edge. It was then impacted again, brought into this other crater feature, impacted again, and then eventually got to the landing site. So basically trying to tie these all together to try and understand movement of material on the surface of the moon. Like it's one question, when we go and pick up the rock, where did it come from? Did it come from right under your feet? Probably not. So how did it get there? And when did it get there? Are really interesting questions.
You're like an anthropologist, but for moon rocks.
Right.
So really quick, I keep hearing the word, and I might not say this right, because I'm lacking education in geosciences. Magmatic, is that right? Or manmatic? What does that word mean? I keep hearing that, but I don't know what it is.
Formed from magma.
Oh, magma. Oh, got it. Okay, there you go. That makes sense. Perfect. Thank you. Magmatic. Okay, well, Allie from Boulder is asking you the question, what is your favorite rock? Moon, Mars, Earth, or other?
Or other. What's my favorite rock? That's a very good question. I have a lot of favorite rocks. I think right now, my favorite rock is actually an Apollo 14 rock sample. It's probably my favorite right now because myself and my students are currently working on it. But it's very interesting. It's sample number 14311. It is very creepy, and it has a bunch of zircons, which is a certain type of mineral that I use for geochronology. And it's just weird. And so some of my students are trying to understand the history of the sample and understand zircons and their ages and the impact history of this sample. So it's just very unusual. So that's my favorite moon rock right now. And then, most rocks on Earth are very interesting to me, but I think some of the cool rocks from Earth are those mantle xenoliths, we call them. So there's deposits down in like San Carlos, New Mexico, where you basically have chunks of the mantle that have come up in this lava. So you basically have this rock and it's lava, right? And then there's just these big clasts with pyroxene and olivine, these beautiful green mineral clasts on the inside. I think they're spectacular. And they're basically chunks of the mantle that got lifted up. And those are not samples we usually have. And if we could get those of the moon and Mars, those would be very intriguing.
That would be super cool.
Yeah.
So we talked a little bit earlier about isotope ratios, and we mentioned like oxygen and things like that. But Stephen from Arvada wants to know, considering the isotope ratios for titanium from the Apollo samples, how they're so similar between the Earth and the moon, which lunar origin model do you believe is most likely?
Yeah, so this is a very interesting question. So I'll give you a little backstory for the rest of the audience. So the Earth and the moon are isotopically very similar, right? And this is one of the main arguments for the giant impact theory of the moon. So there's many things that you have to explain with the moon. First of all, our moon is large compared to Earth, right? If you look at the comparative size between the moons of Mars and Mars or any other planetary system, the moons are a lot smaller. So we have to explain, why is our moon really big? We have to explain, why is it chemically or isotopically identical in many systems, or if there are some systems that vary, but not by very much. And then we also have to explain the angular momentum, right? We have really high angular momentum, which means there's a lot of energy in this system. And the chemistry is kind of the key constraint there, right? You can explain a lot of the other factors by having, high spinning moon or proto-Earth that has a blob of the moon come off. But basically, like, in order to explain all of these elements, this giant impact theory is kind of the one that we're all leaning towards at the moment, right? And in this, it's basically you have the proto-Earth, or the Earth prior to the moon, and it gets hit by a Mars-sized object. And as a result of that, that's very high energy, right? So you can explain angular momentum, sometimes too high energy, but we're always dealing with that. You create a debris disk that is very hot, and the material will mix, and so you can homogenize potentially the material between the proto-Earth and the impactor. So if there's a chemical signature difference between the two, you can mix them up. But if they're forming in the same place in the solar system, they're probably chemically similar anyways. And that also explains the large size, right? The moon that forms out of that can be kind of big. Can explain other things too, like, why is the moon depleted in volatiles? By those, I mean those that go into the gas phase when they heat up. Like, why is there not a lot of water? Well, if you're in a really hot debris disk out in space, you're going to lose all of those. So there's all these different aspects of that model that make it very favorable. There are things that are complicated and aren't perfectly answered by that, but right now, giant impact theory of lunar formation is I think the one we are all leaning towards.
As far as I'm aware, there's no like close second, right? Like that's pretty unanimously like the option. There's no one out there being like, right, but what if we did this, or what if this happened? And everyone's like, oh no, that he's got a point.
Yeah, there's interesting things to think about with there's one of the key issues used to be angular momentum, and that if you had things like the fission model where you had a blob fly off, you had way too much angular momentum. There's no way to get around that. Now there was a paper a few years ago that discovered this resonance, basically a way to dump energy into the sun, but basically energy from the sun moon system the Earth moon system into the sun moon system, right? So there's been mutterings about that, but nothing serious.
So you just said the words sun moon system, which is probably a whole
sun Earth
kind of word.
So
sorry,
I meant Earth moon system to sun Earth system. Sorry,
oh, got it. Okay, that makes sense. I was about to be like, well, hold up. But yeah. Extremely complicated system between the sun and the moon. Right, because the moon orbits the Earth and the Earth orbits the sun. All right, cool.
And there's ways when they kind of all line up where you can transfer that momentum. Yeah.
Got it. Very cool. And I think that concludes the questions that we had from Capcom Q&A. So thank you very much, Austin, Dee, Ali, and Stephen. And Charlotte, we saw your question, but we kind of answered it during the base portion of the interview. And so thanks all of you very much for sending in your questions. And we always like to close episodes off by asking you, Carolyn, how you got to where you are. It's always interesting hearing the backstory of how, these experts in fields ended up being experts in their fields.
Yeah, so how far back? No, I was kidding. So I actually started out my undergrad at the University of Maryland in College Park, which is right outside of DC, in aerospace engineering. And for many reasons, I decided to go the science route instead of the engineering route. One reason being that, the scientists are the ones that are asking the questions and getting the answers, and then the engineers are the ones that are helping you figure out how to get there. And I wanted to ask the questions more than doing the designing of getting how to get there. So I switched majors and majored in astronomy for my undergrad. And then for my undergrad research projects, I actually did work looking at extrasolar planets, or trying to understand what extrasolar planets would look like using the epoxy spacecraft, which was the spacecraft that was left over after the Deep Impact mission. And I kind of realized that I didn't want to look through a telescope for my research. And so I was trying to figure out what I wanted to do. And my undergrad research mentor, Lucy McFadden, handed me an iron meteorite and said, "This is from the core of a body that no longer exists." And I was hooked. And I realized that doing work with samples in a lab here was more interesting and fulfilling to me. So I had said, okay, so how do I do this instead? And the people that study meteorites are geochemists. And so I went to grad school at the University of California, Los Angeles, and got my master's and PhD in geochemistry, working on Apollo samples. And then after that, I did my postdoc, as I said before, at Lawrence Livermore National Lab, doing work also in cosmochemistry on Martian and lunar samples, and also starting to do work in nuclear forensics. And then I came to CU, almost over 2 years ago, 2.5 years ago, as a researcher. And then I just started this semester as an assistant professor. So it's kind of my long history of getting here.
Very cool.
Yeah.
Okay, well, that's all the questions that we had for you. Thank you so much for joining us today, Carolyn. It was a blast chatting with you.
Yeah, thanks for having me. This was a lot of fun.
All right, and that concludes our episode of A View from Earth for today. We'd like to thank Carolyn Crow again, Dr. Carolyn Crow, for giving us her time and telling us all about geochemistry and some upcoming missions that we're really looking forward to. Stay tuned for next week. We'll be talking with Andrew Novick, who is a NIST Time Lord. And NIST, by the way, is a place in Boulder that sets the time for the entire United States of America. He also helps maintain time.gov. So if you ever need to know the time, you can just go to time.gov. Anyways, we're going to be talking with him about how time works. And in the meantime, you can always check out our website, colorado.edu/Fiske. And there you can find a whole bunch of fun stuff. But you can do two things primarily. Number one, you can send us your questions for us to pass on to our experts, so you can hear your question on the air. And that's kind of, a cool opportunity to ask someone who really knows what they're talking about a question that you've been dying to learn the answer to. The other thing that you can do from our website is help support our podcast by making a donation to the Fiske Planetarium. These are hard times, and right now stuff is tight, and we really appreciate anyone who is able to contribute to the future success of A View from Earth. This podcast is on YouTube, SoundCloud, Apple Podcasts, and Spotify. And we here at A View from Earth would like to thank you for listening.